So if you let n be a 0, you're going to get x to the 0, which is a 1. If n is a 1, you're going to get x to the first. If it's 2, you're going to get an x squared, so on and so forth. So what I want to do is we're going to graph these on our calculator. And now it's going to take forever. I forgot to do this. You'll see this one tomorrow. All right, so if I go ahead and graph y equals 1, that was the first term in that polynomial. All right, we all know that's a horizontal line. If I go to the next one, that's going to graph 1 plus x. That was the second one. Now it's a line. Notice how they both go through 0, though. So as we start talking about centered at 0, notice how there's no shifts in any of these. That's why these are all going through 0. So that's kind of what it means in some ways to be centered at 0. If I then go through and graph 1 plus x, and then I add the next term to this, so x squared, this is now my graph. So that's the first thing that I asked you to do on it. What we then are just going to do, I'm going to continue to add a few more terms. So 1 plus x squared, and then x cubed. And let's do one more. 1 plus. I was wondering, I was just thinking in my head, like, hope I'm doing these right, because I'm not really looking. Oh, thank you. Plus x cubed. All right, and then x to the fourth. Okay, so that was the last one. That's the last one. So kind of look at what they're doing, because then I ask you a series of questions on all of these. First, notice how every single one of them goes through 0. So if we're centered at 0, wherever we're centered at, we're definitely going to cross that x value. So it says, what happens on the interval of a negative 1 to 1? So if we kind of look at this, notice how in the interval of a negative 1 to 1, don't these all, if you kind of think of a string that would unravel, doesn't it appear over that interval that these are all kind of getting right on top of each other, right? They're all, what we're going to say, they basically converge at that interval. Okay, so they're all converging upon each other within this interval. If I go outside of that interval, though, notice how they all kind of take off in their own direction. So once I get past a negative 1 and a positive 1, they all kind of do their own thing. So as long as they kind of stay within that window, they're friendly with each other. If I then ask you, what is the sum of the series? So remember, the sum of a geometric series is whatever the first term is divided by 1 minus our ratio. Isn't this guy here really a geometric series? If I ask you what your common ratio is, aren't we multiplying over and over and over again by the variable x? So if we put that in here, the first term in this series would have been a 1. And then I do 1 minus my ratio. Instead of this being a number like it was in our previous couple sections, it's now a variable. So this is actually the sum of that series. What I'm then going to do is graph the equation for that sum. So now I'm going to graph this along with all of these guys. So if I now go back to my calculator, and this is important to understand because it's really kind of the basis for a lot of the stuff we do over this week. If I now graph 1 over 1 minus x, and now graph that, notice within the interval of it was this orange one. Didn't that orange one basically run right on top of all of these other ones? When I just used 1, so if I would have just graphed the first one, so if I turn off all of these other ones, did that first one, so if I just graphed the horizontal line, did it really look much like the sum of that? No. But with each one that I add, so if I now turn this one off and turn this one on, now a little bit longer period of time, it kind of looks like it. And as we continue to add them until we get all the way down to this one, if I turn this one back on, the more and more terms I add, doesn't that more closely reflect and produce the sum of that series? So the more and more of these we do, so last one, hopefully we're understanding this at this point. Let's say I add one more. This should now produce even more of the y sub 6 question when I do plus x to the 5th power. All right, so now that green one was the 6th power. Notice how you can't even distinguish between them. It's going to be more and more accurate in graphing the sum with the more and more terms that we put in there. Okay? So that's what we kind of want to understand about this. So then, why is it only working in this interval? Why are they only converging upon that? Well, isn't that a geometric series? And didn't we say in a geometric series, the only way we can converge if our radius, absolute value is less than 1? Well, isn't our radius, in this case, the absolute value taking of x, isn't that our radius less than 1? So then if you rethink, remember old absolute value inequalities, how we set those up, doesn't that mean x has to fall in between a -1 and a 1? So as long as I stick within this window, I could plug in any x value into this general term, and I'm going to get a series that converges, and we're going to converge to this function. All right, that kind of makes some sense here. All right, we're just going to do one of these because in grand scheme of things, this is not a big deal. Go down to, maybe we'll do 2. Go to number 1 first. If I ask you what the sum of this series would have been, understanding that this is our sum formula, wouldn't the first term have been 1? And then wouldn't our radius, if I now have a radius, since this is 1 plus x, wouldn't our radius have had to have been a -x? So what that would be, the 1 over 1 plus x, would have had to have been an initial term of 1, and then we would have been multiplying by a -x over and over again until we get to the general term, and all that would have been was a -x to the nth power. We're just multiplying by -x over and over and over again. So that's if it's a -x. 3 is the one I wanted to see too, just so we understand how this interval is now different than the first couple. Doesn't our ratio in this one, since it should be 1, I have a 1, it should be minus, I have the minus. The next thing should be my ratio. So isn't my ratio here 2x? Well, if my ratio is 2x, I know then that this geometric power series, as long as this stays less than a 1, we should converge. So if we set up this old absolute value inequality, divide, that's why our interval of convergence, where this would produce, if we write out all those terms, would produce this graph as long as we stay within this little window here. All right. 3, 4, even as you look at them later, just completely cross them out, so don't think you have to revisit those. Not anything that I'm going to go after soon. All right, so now go to, which one do I want to start with? Go to number 1 here. Yeah, go to number 1. And again, I'll kind of explain all this. We had some more time. We dive into that a little bit. Go to number 1, and we're going to make sense of it here. And since it's our first one, let's get rid of the negative. Let's not add that layer into this. You don't have it already? Okay, perfect. So what we were trying to find out right now, if this was our series, what values of x would this thing converge for? All right. So the way we're going to set this up, what we're basically going to be doing is the ratio test. So go ahead and set up our ratio test. So that's your n+1 series divided by the original series, which is the same as multiplying by its reciprocal. The difference being, since we now want an interval of convergence, that's what the absolute value means. It's within a certain little radius on either direction. So we're going to do the absolute value of our ratio test. So let's split this up. Eventually we're going to stop doing this because you're going to do this a number of times. But x to the n+1 is really x to the n times x. And then I'd have an n and then x to the n. The x to the n's then cancel. And what we are left with is an x times n in the numerator and then an n plus 1 in our denominator. We all know then in the ratio test, because most of us did the ratio test pretty well on that quiz, we then at the end, once we have it simplified, want to find that limit as n goes to infinity. So a little weird, the first one, but nothing crazy. In fact, let me give you one so you think this is not crazy. If this was 3 times n over n plus a 1, would we all agree that this has a limit of 3? Because of the exponents are 1, you look at the coefficients. That's really what we have here. Here's an exponent of 1, a power of 1, so their coefficients should be your limit. The coefficient in the numerator is x, the coefficient in your denominator is a 1, so that limit really is just an x. Now, when we would have done this yesterday on your little quiz, this was always a number. So if it was like a 1/2, then we would say, yeah, it converges because your p is less than a 1. If it was 3/2, you would say it diverges. Well, now it's a variable. It could be a bunch of different values. So what we know when we do the ratio test, which we just did throughout all of this, as long as this is less than 1, we're going to converge. So any number whose absolute value is less than 1 is going to work. So solve this, rewrite this as an interval. So write it as an inequality. That any number is going to work. Right? So Maddie, give me a number between a -1 and 1.
0.
Don't give me 0. Other than 0.
-1/2.
All right. So if I give a -1/2 to the n, what that is telling me is if we go through all of our tests here, so let me write this as a -1 to the n over 2 to the n divided by n, isn't this really a -1 to the n over n times 2 to the n? If we go through and test this right here, so what we did yesterday, this is guaranteed to converge. Any number in this interval is going to work because it satisfied this right here, that our ratio test has a value less than a 1. All right. However, what happens in the ratio test, and we did this a little bit today when I went over the quiz, what if this equaled 1? What did that mean? Did it converge or diverge? Or neither?
Neither, no.
Yeah, we don't know. So if it equaled 1, could it have worked? Yeah, it could have worked, right? So the two places where it could have equaled 1 are your endpoints. So doesn't 1, if I plug in a 1 right here, doesn't that equal a 1? So it may or may not work. So what we have to do is then test our endpoints. So what we're going to do, this is an at. So if I say at x equals a1, what we want to do is to take this endpoint, plug it in, and see if it creates a series that would converge. So if I do a 1 to the n over n, isn't 1 to the n really just a 1 over an n? So at this endpoint right here, when I plug that in, did that create a series that converges? No. So we would say real quick here that this is going to diverge. That is one everybody should know at this point, the harmonic series. So we don't do anything with that one. Well, the other place that this could equal 1 is if x is a positive 1, then it actually equals 1. So we don't necessarily know if that works or not. So the same thing. We now need to take this -1, plug it in, and see what it produces. So at the x value of a -1, let your x be a -1. So we're just going to get a -1 to the n over an n. Does this guy converge? What?
I don't think so. No.
You don't think so? Anybody think so?
Yeah.
Does converge, right? Now, for what we're going to be specific here, this would converge conditionally. All right, why'd you say yes, Luke?
Because you could just turn that into an alternating series, and then but then if you get rid of the -1, that would just be a simple harmonic.
Good. So what we're looking at here is the alternating harmonic series, and that's one, again, you don't really need to say much more than that. It's understood that the alternating harmonic series converges conditionally. So -1 works. So what we have to then do is come over to this interval, and we need to include the -1 for producing a series that's going to work. This is what is then called our interval, so you get to a test, 100% chance you have to do one or two of these. 2 weeks from today, those taking it on that day, 100% of the chance you're going to have to do one of these. That's your interval of convergence. Any x value in here plugged into this series will make that thing work. You will also sometimes get asked your radius of convergence. So what that alludes to is, where are we centered at? So if I go back, let's make this a little less messy. All right, does this x have any shifts in it? Meaning, do I have like an x plus a 6 to the nth power? No. So you're centered at 0. So all of these terms, if we start writing out this polynomial, are going to go through 0. Look, if I start at 0 and I went to 1 on the right and a negative 1 on the left, didn't we just go 1 in either direction? So you would say that your radius of convergence is a 1. That is the other thing that sometimes we'll get asked with this. Okay? All right, so we're not really going to, these take a little bit of time. As you can see, there's a lot here. So it's going to, like, this is x plus 5, right? So this means x equals 5 is where we're centered. Let's say we do our whole process up here, and let's say we get, I don't know, -3 and -7. If I'm centered at a -5, isn't -3 2 to the right? -7 is 2 to the left. So we went 2 each direction. That's our radius of convergence. If I'm centered at 0, I'll converge 2 units to the left or right of where everything is going to intersect. Okay. So you'll see number 3. Yeah, we'll do that one. Okay, we've got to stop. I'll bring this tomorrow. We'll jump around a little bit, make sure that you see the ones that we really need to make sure we see. But if you're at home, you're free to check out. We're not going to get another one of these done. It'll take a little while. If you have any issues with the quiz, if you're still not sure what I wrote, just let me know. You have a minute now to do that.